Welcome. The topic for this presentation is open-air theater design. Introduction. The purpose of theater is to provide recreation to people. The theater is a branch of the performing arts and it is concerned with the acting out stories in front of the audience. Open-air theater is a space in which a performance may be given before an audience, and as the name suggests, it does not have any roof structure. The word is from the Greek theatron, a place of seeing. A theater usually has a stage area where the performance itself takes place. Since ancient times, the evolving design of theaters has been determined largely by the spectator's physical requirements for seeing and hearing the performers and by the changing nature of the activity presented. Here we have a few examples of open-air theaters from around the globe. The first one is Teatro Antico di Taormina, Taormina, Sicily, Italy. Second is Vondelpark Open Air Theatre, Amsterdam, Netherlands. Third is Regent's Park Open Air Theatre, London, England. Fourth is Greek Theatre of Syracuse, Sicily, Italy. Fifth is Toga Open Air Theatre, Toga Art Park, Toyama Prefecture, Japan. The last one is Minack Theatre, Cornwall, UK. In order to design an open-air theatre, one must recognize how sound is affected by meteorological conditions and topography. When we talk about meteorological conditions, we are trying to see how the atmospheric conditions, like temperature, wind flow, and humidity, etc., affect sound. Spaces where it is not covered, or it does not come under room acoustics, we have to take care of the noise, which is created at some point, and is carried to another point or location, where some good acoustical quality is required, like open-air theater. The influence of topographical conditions, particularly the slopes, undulations, then the plantations and the vegetations, and how sound behaves in such environments. To understand the various influences of meteorological conditions over propagation of sound, we have to go through the following four segments. First, sound absorption by air. Second, effect of temperature on sound. Third, effect of humidity on sound. Fourth, influence of wind speed on sound. The air absorption, as per the curve, the frequency of 100 Hz is minimally absorbed in air, 1 dB per kilometer, whereas a frequency of 10,000 Hz is absorbed, up to 100 dB per kilometer of travel of sound. So we see that, it is not necessarily true, that all frequencies get absorbed equally, while passing through the air. High-frequency wavelengths are more easily absorbed by the molecules of air. That is why, there is a significant reduction of sound of higher frequencies, whereas, there is a negligible reduction of sound, when it is of the lower order frequency, considering that, the distance traveled is the same. Sound absorption decreases with increasing humidity, whereas dry air has the least absorption. When a sound of high-frequency band is moving through air, all of it will not be reaching the listener at the same level, but they will be absorbed at different levels while passing through the air. #low-frequency sound travels the farthest, whereas, higher-frequency sounds do not move to the desired extent. How the temperature changes the speed of sound. Here you see a graph which has been drawn while a sound of 1000 Hz is passing through the air. At 20 degrees Celsius, we see speed equals 343 meters per second precisely. Formula which has been derived, V equals 343 meters per second plus 0.6 times T minus 20, where T is the temperature in degrees centigrade, which is the gradient. So, at T equals 20 degrees Celsius, the velocity of sound is 343 meters per second. And for every 1 degree Celsius change of temperature, the change in speed is by 0.6 meters per second. 0.6 meters per degree centigrade change of temperature is a big amount when we talk in terms of the wavelength of sound. In feet, this comes around 2 feet per second. Humidity, more or less up to 30 degrees Celsius, it is behaving in the same manner as temperature. But the temperature and humidity do affect differently above this. The red line represents 100% humidity has shifted from the black line represents 0% humidity mostly above 30 degrees Celsius till 50 degrees Celsius. So, the gradient is higher when the humidity is more. We have to account for these changes in speed when we are doing any outdoor space design. When it is daytime, the ground is warm, and the atmosphere above it is cool. The sound speed at a position much above the ground will be lower. Whereas, the sound speed below near the ground will be higher. At the lower portion near the ground, the sound will be moving faster as compared to the upper part. If the direction is this rightward, there will be a change or the sound wave will move upward. This will lead to a no-sound zone in this particular area rightwards of the source. If a receiver is standing here, he will not get any sound. This area becomes a sound shadow area. Thus, even if the source is close, the people around may not be receiving the sound. Whereas, the sound energy is drifting upward. This is called temperature lapse or superadiabatic. So, temperature gradient leads to the bending up and down of sound waves, and during the daytime, the ground being warmer, the sound moves upwards, creating sound shadow zones in regions close to the ground. The opposite phenomenon or an inversion happens during nighttime. During nighttime, the ground surface is cooler, whereas, the surface or the atmosphere above is warmer, where the sound tries to move faster, leading to an inversion. You can see, here the sound is bending downwards or more towards the ground. And this is called temperature inversion. This happens mostly during the nighttime when the temperature is the coolest right next to the ground and warmer as you increase in height above. This downward refraction of sound helps people hear conversations even across water bodies or across long distances, particularly at nighttime. Hence, distant sounds are usually heard at nighttimes rather than daytimes, particularly because of this temperature inversion. This is what you see as a summary, that hot air moves faster, and when it is nighttime, it bends towards the ground, or towards the receiver from the source. And during the daytime, the hot air drifts the sound upward, which leaves the receiver with very less sound. Influence of wind speed on sound. The effect of wind on sound outdoors is a complex phenomenon. Downwind from the source, sound is normally bent toward the ground, increasing its sound level. Upwind, sound is bent upward, causing a shadow zone where the sound level will be reduced. For example, at distances greater than 500 feet, as shown below, the upwind mid-frequency attenuation can be about 10 decibels for winds of 10 miles per hour. However, a reversal of wind direction can increase the sound level by about 10 decibels at the same location. Consequently, do not rely on attenuation from the wind when designing outdoor noise control measures. When the wind is flowing, it is found out that the wind speed varies logarithmically up to a certain height, say around 30 to 100 meters, depending on the speed of the wind. At the initial stage, it moves very rapidly. It is flowing, and after a certain height, it becomes steady. It is drifted upwards by the wind when the sound wave is traveling in a direction opposite to that of the wind flow. Since the source is producing sound in all directions, a portion of the sound which is in the opposite direction to that of the wind gets drifted up. And on drifting up, some low sound pressure zones are automatically created in the opposite direction, and the sound bends down to fill up those spaces. So as a rule, sound wave bends towards regions of lower sound speed. We see that this drifting up and bending down causes a refractive effect of sound, particularly when the wind is present and the sound is moving steadily, against the wind. Thus in the direction of the wind speed gets summed up to the sound speed. But when the sound is moving opposite to the wind direction, it gets subtracted. So, when the source is at A, and the wind is blowing from left to right direction. At wind speed, 3 meters per second, say the sound is produced in the direction opposite to the wind. If we consider the speed of sound, 340 meters per second, the wind speed, 3 meters per second, gets subtracted from it. So, here we are considering that the wind is steadily flowing, and hence we are just subtracting the values of the speed at the particular unit. Here the unit is meters per second, so 340 minus 3 is 337 meters per second. On the other hand, the sound which is moving in the same direction as that of the wind, that particular sound energy will be moving faster, 340 plus 3 is 343 meters per second. When we are trying to speak or sing something in open space or open air, we have to think of the combined effect from wind, humidity, temperature changes, air absorption. We have to account for each of them in our calculations and try to look into the overall phenomena, how the speed of sound gets affected, because, with speed of sound, the distribution of it will be considered. To comprehend the influences of topographical conditions on sound, we have to examine the following two components. How sound behaves on the slopes along hills and how plantation and vegetation affects sound. Here is a hillock or hill as shown, and a sound is produced at one end of the hill, which is not at all reaching, or a very small amount is reaching, to the house or the receiver at the other side of the hillock. If we had a house here on this left side marked P, sufficient amount of sound would have reached the receivers or the inmates in this house, but on the other slope on the right side, no one can receive the sound. It is only the diffracted sound which is reaching this particular area. If you look back into history, the amphitheaters were usually located in regions along the hill slopes, which were opposite to the sources of sound. The noise which is created in this area, marked Y, does not travel into this area much, marked Z, and this area, Z, is considered as a quieter area. We, as architects, also need to seek our open-air theater locations in such areas where this kind of a hillock or a barrier could be artificially created or planned so that the sound source or noise from the other side of the slope does not affect our proposed location for the theater. Unfortunately, we may not always get a hillside for our design, but a plateau situation, which the second picture shows, is very common, where the sound or noise source is at point A. Some diffracted sound, or maybe little more than the previous case, is reaching this particular area on the slope, which could be further treated by landscape elements. This house is not receiving much amount of sound as desired, which it must have received if the house had been located somewhere in this area marked X. This downhill is an appropriate location for seeking areas where we need to build our structure, which needs acoustical quality. Here is another case. You may have a sound source downhill, marked B, and the source sound is moving upward but not affecting this particular area on the plateau, marked K. This particular above plateau area, marked K, and beyond is also a good location, provided the sound or noise sources are in this particular downhill area marked B. Thus we can take advantage of being at a raised level, so that sound from the roadside or industries can be curtailed, and we can plan for an acoustical space at an elevated level. The fact is that change of levels can change the amount of sound, whether desired or not, depending on where you can choose your location. We should keep in mind that we need not always adopt measures, but by taking advantage of the topography, we can plan our entire set of buildings or set of requirements that have to be fitted into a given site. Now we shall take a look at how plantation and vegetation affects sound. Plantations and vegetation absorb sound. And, hence they must be taken into account when we are doing some outdoor design, where noise, which is basically undesirable sound, has to be reduced. In picture A, the sound is coming from the source at the left direction, having a high sound pressure level, and passes through multiple reflections between the leaves and the branches and finally comes out from the other end with a low pressure level. Now, coming to questions. About how much, how many, and what type of vegetation are to be planted? If you can plan a dense plantation with different types of plants or foliages, then the amount of absorption will be better. Observe the pictures, C and D. It has been proved that, up to 5 to 10 decibels or even more can be absorbed by dense foliages of around 15 to 30 meters thick. Observe the picture, B. Grass or soft ground absorbs a lot of sound. There may be areas where plantations are not present, but if the sound falls onto the grass, that is, the angle of incidence becomes such that it encounters the grass surface or soft ground covered surface, then a significant amount of high decibel sound gets absorbed. A few key points to note here. 1. Dense belts of trees 15 to 30 meters absorbs sound 5 to 10 decibels. Cook and V. Haverbeek 1970. Leonard and Parr 1972. Riethoff 1975. 2. Dense belts can reduce noise by 6 decibels. Huttert 1990. 3. Different types of leaves provide better sound absorption. 4. Rustling of leaves may help to mask noise. 5. Noise reduction tends to increase with tree height up to 10 to 12 meters. 6. Height of sound source and distance from source is also important. The rustling of leaves may help mask the noise. Furthermore, dense belts and different types of leaves provide better sound absorption. If we have trees planned and landscaped with different foliage, like deciduous, evergreen, or coniferous ones, then it would improve the acoustical situation. Since we have the provision of growing plantations, we can create a belt of trees to check noise or unwanted sound, and we know that rustling of the leaves helps mask the noise. If the noises are of similar frequencies, then the masking of it can happen due to the rustling of the leaves and the branches. Noise reduction tends to increase with the height of the tree. Experimental researches say that trees up to the height of up to 10 to 12 meters are effective in noise reduction. However, canopies at higher levels would not provide significant noise reduction effects. Finally, the height of the sound source and the receiver's distance from the source is also vital. With the understanding of the topographical and meteorological effects, we go back into the early Greeks and the Romans and understand how did they plan. We will see that they had planned everything in the open air, they took advantage of direct sound reaching their audience, they did not have anything to reinforce sound, and there was no concept of reverberation, neither at that time, nor it happens in open-air theaters as well. So, there is no reverberation, we do not have any enclosure effect. They had seating plans, which were formed like a segmented circle, more than 180 degrees, mostly on hillsides facing the sea. On hillsides, the noise from the other side of the hill does not reach, and that the audience must be facing the sea, speakers back towards the sea. This shows the importance of the wind direction. They accounted for the meteorological conditions as well as the topographical condition, way back. They had steeply raked the seats and obviously, had low background sound because they were on the other side of the hill, opposite the noise source. And, all these increased the intelligibility, and you can see the source sound is directly reaching the audience. We can characterize the Greek theaters by these points, such as these theaters were open air. Only direct sound propagation was used. These theaters were made on steep slopes. And obviously there was no sound reinforcement. Finally, a minimal reverberation can be heard in those locations. Here we will see the example pictures of an ancient Greek theater of Epidaurus, dated 330 BC. This is Epidaurus, which was unearthed. It had 34 rows initially, which you see here, and later 21 more rows were added, and it had a radius of 60 meters (186 feet). The sound reached at the farthest point, which has been explored further by researchers of Georgia Institute of Technology in 2007. The researchers from the Georgia Institute of Technology found that limestone seats filter out low-frequency sounds which were not desired, and they allowed or amplified the high-frequency sounds from the stage. These limestone seats are considered as corrugated surfaces, which acted as filters to emphasize certain frequencies. The designers at that time specifically used the limestone material and this particular corrugated or folded structure to get the advantage of cutting down low-frequency sound, due to footfalls of the crowds, etc., and to amplify the high-frequency sound, which was desired. The prevailing wind direction was also considered, and that was flowing from the direction of the stage towards the audience. That also helped in getting better sound quality. The steep slope helped the sound to move to the farthest point, which was around 60 meters away. The dense foliages at the back, which did not allow sound to reflect back, rather, sound was absorbed within the foliages. Although this is a present view, it is believed that during those times, too, such kind of foliage existed and the trees could absorb the unwanted or delayed reflection, which would have otherwise disturbed the sound quality in this amphitheater. The Romans also followed the seating arc limited to 180 degrees, and used arch features instead of hill slopes. They had a high guard wall which prevented the sound or noise outside from entering the amphitheater area. This was adopted by the Greeks along the hill slope. The Romans created an arched facade to cover or enclose the sound or noise that could disturb the performance, that is the desired sound from the performers. Romans had a high wall at the back to cut down the noise from outside. They added the stagehouse, and the raised seating area in front of the stage, and had huge awnings to shade the patrons, and these helped in early reflections of sound. Roman theaters, like the Colosseum, or the Aspendus, has these features. The colonnades at the back which helped in cutting down the noise. At the front, on the stage area, there was a high wall, which also helped to cut down sound, and the seating area is similarly planned like the Greeks. All these helped in getting a better acoustical quality for these spaces, but these were done several centuries back. The understanding which we have formed from the meteorological conditions and the topographical conditions were adopted. We can conclude that minimization of external noise is required, and that could be achieved by selecting sites along hill slopes or at an elevated level, or by shielding the site with barriers or walls which could check the external noise. Sufficient directly propagated sound has to be encouraged since there are neither much reflections nor diffusion, diffraction, or anything playing a role here in propagating the sound. And it is the direct sound which needs to reach, and for that, we can take into account the wind direction. The orientation is crucial, which should account for the wind direction. To utilize sound from the first reflections, we can plan a canopy over the stage, as the Romans did. Thus, when we look into the open-air designs, we must keep in mind that first reflections can be utilized by providing some sort of a canopy over the stage so that the performers can receive back their own sounds as feedback, and also to spread the sound more towards the audience. Moreover, the steps along the hill slopes also helped in sound reflection, as seen in the limestone steps of the Epidaurus. Materials like limestone can be used in corrugated fashion so that they can help in first reflections. Control of late reflections and elimination of echoes by having proper plantations at the back can help in checking late reflections. You can also propose or build a wall at the back to allow the sound to move towards the trees and vegetation, and it can check the external noise. Alignment for acoustical advantages, such as orientation towards the wind direction considering the noise source location, are also to be taken into account when we think of planning for an open-air theater. We have analyzed the climatic conditions, topography and landscape. Then we have learned how the ancient Greeks and Romans have created many marvelous theaters. Now we shall discuss the open-air theater design principles of modern days. To begin with the discussion, we have not made a miraculous difference in design concepts from what the Greeks or the Romans did. We are trying to follow them with few additions and alterations to their concepts. The points to be considered are site location, orientation, seating plan and acoustical plan. As we had already learnt the meteorological and topographical conditions, we will try to see where to locate and how to locate an open-air theater in a given site. Unlike earlier times, we do not have an abundance of land or hill slopes, where we can freely locate these open-air theaters as per desire, in the middle of the city or elsewhere. We also have to look into the orientation, as Vitruvius Pollio had already said that if the audience faces the sun, they will find it difficult to observe the performances. The seating arrangements, which were initially started by the Greeks and Romans, are to be decided. We need to acknowledge their thoughts and would mostly follow their principles. Coming to the acoustical plan, we have added certain features which were possibly unavailable during those times, and we have tried to improve the listening conditions while building our open-air theaters in cities or urban fields. The site location, our first objective is to minimize the external noise. Because, if we are in the middle of a city, we can expect a lot of noise from the roadsides or from other buildings, which can add to the existing noise. To keep away the noise, we have to use buffers. The noise level should be mandatorily below 40 decibels. We also need to know the topographical aspects. We have to find a quiet zone in a flat site or somewhere downhill of the slope if the site has a terrain, or raised locations within the site. That zone should fall in the sound shadow area considering where the noise source is. When we think of locating an open-air theater in an urbanscape, if the site is like rectangular plot, as seen in the picture, and having adjacent roads, we can see that a quiet area forms at this particular zone, away from the road. But if you check out the other activities in the adjoining plots, you will understand that these may be also creating some noise. Though maintaining a setback from the road can protect our proposed location from the roadside noise, we may end up with more noise from the activities on the adjoining sites. Firstly, we need to understand where the site is located and the adjacent conditions. That may probably have some influence or can add to the prevailing external noise for that particular site. In that case, we may consider the central part of the site as being sufficiently distant as far as noise sources from outside are concerned. This decision has to be taken first before we start designing our open-air theater. Now assume we have the adjoining road and other parameters, and it is quiet on the adjacent plots, then we can plan to cut down the noise from the road by considering making a row of buildings that would remain functionally unaffected when placed along the noisy road. These buildings act as a reflector to the sound which is created in the road and does not allow the sound to enter into the open-air theater zone. Furthermore, there is an addition of a backstage, a wall behind the stage, which can also prevent the sound or external noise from entering into this particular area. Thus, providing a noise-free zone within the site by creating a line of buildings or a back wall behind the stage or both to protect the OAT from the external noise. Similarly, by planting a few rows of trees of different sizes of foliages as discussed previously, we can get a reduction in noise level. By maintaining shrubbery heights of up to 10 to 12 meters, we can prevent the incoming noise and allow the OAT to be a noise-free zone. For the main theater, usually, with capacities of up to 600, we do not require any amplification of the sound and can carry on with the performer's own voice. Coming to the orientation, the time of the performance is very much important, along with it, the study of the sun path is also crucial. The concepts of awnings and shadings, which the Romans had utilized around 2000 years ago, could be adopted. In case the performances are scheduled during daytime, it is imperative that the audience must not be facing the sun. Suppose we have some religious or youth gatherings, where there is no open-air theater, but just an open field where the ground level is flat all along. We have to address the effect of temperature. Recall that the temperature on the ground surface is higher, and that helps bend the sound on the upper side, creating sound shadow areas at the back. It may happen that the audience members seated at the back side are not getting any sound. This occurs not because the actor on the stage is speaking with a low unamplified voice, but because of the effect of temperature. We must also consider preventing late reflections, because those are the causes of echoes. We must avoid buildings at the backdrops, that is, at the back of the audience. There should not exist any hard surfaces like tall buildings at the end, which will, otherwise, reflect the sound and generate unwanted echoes. Historically, the Greek theaters were characterized by open air, with direct sound moving to the top, up to 60 meters. They had steep slopes of 2:1 gradient. There was no sound reinforcement during those times, and there was no concept of reverberation, which were very minimal in that kind of structures. The same features are adopted for our open-air theaters too. Greek theaters were characterized by the following points. 1. Open air. 2. Direct sound. 3. Steep slope. 4. No sound reinforcement. 5. Minimal reverberation. The Greeks and Romans also accounted for the wind direction, which we had seen that if the speech is along the wind direction, it helps the sound to reach to the farthest audience. Accounting the wind direction for acoustical advantage has to be kept in mind. Sufficient directly propagated sound has to reach the audience, and we do not consider a very steep slope. However, this particular slope should be at least 12 degrees. A hard surface at the back of the stage can help reflected sound to move towards the audience. If the source on stage, then reflected sound from that area can move towards the audience, with help from the wall at the back of the stage. Some amount of sound also can move towards the floor, because in an open-air theater, there are very less chances of getting early reflections or helpful reflections to reinforce the source sound. We have already seen that the limestone steps at Epidaurus, which had corrugated or folded surfaces, helped in multiple reflections of the sound. The same concept can be adopted in our design. Stepped seating allows sound reflection from the proscenium side, or the stage side. To get sufficient directly propagated sound, we need compact planning. The sound from the first reflections is always welcome. Only the direct sound will not be sufficient to reach the last row of seats. We need the first reflections also, such that they can create better sound quality within the space. Sound bounces back and forth from the vertical risers and the stage wall. Hence, we can take advantage of these as creating first reflections. These help in creating a blended sound within the open-air theater. The major problem here is that we are in the open air, we cannot follow the principles of room acoustics, hence concepts of reflection from the ceiling or the side walls are no more prevalent. While trying to take advantage of whatever reflecting areas that exist to enable first reflections for better hearing or better blending of the sound, delayed reflections may happen from the back wall, so if we plan for a back wall at the end of the OAT, then we have to check the delayed reflections or the echoes. If the back wall is present, it should be limited to a particular height. Scattered energy is required to fill in the gaps between the few first reflections happening. And, these scattered energies from the reflected sounds coming from the treads and the risers, in audience seating area, can be utilized. The gaps, where there are no audiences, help in accumulating this scattered energy for better hearing or better quality of sound. Diffraction and scattering from seating areas help to achieve a smooth decay curve. The decay curve and the reverberation time is the summation of many early reflections. This does not happen to create a blended sound. This diffracted and scattered sound adds on to the first reflections to achieve a smooth sound decay curve, creating a blended sound within the audience area. Here, we see how the sound is moving. The direct lines are shown in pink, and the reflected sound is shown in blue. By taking advantage of the back wall and the risers of seats, some amount of early reflections occur, to reinforce the source sound. Additionally, these corrugated seats help to get blended sound of better quality. However, if we have a flat slope, these multiple reflections does not happen, it is like an inverted cone situation. In this case, whatever sound that strikes the sloped surface, gets reflected up towards the open sky. So, if we think of a flat slope, then you would be ending up with bad quality of sound. The inverted cone effect directs the sound upwards, causing loss of energy, and fewer early or first reflections occur, and thus creates an undesired design. But if you plan a mound for the audience area, keeping it very green, the undulations there will help in scattering sound towards the audience. Some pointers to remember regarding seating area. Sound reflection from the tires of benches, if at a distance, produces a sustained echo. Pitch can be determined by the distance separating the risers. This causes distortion in some frequencies and affects sound quality. In OAT, the frequency-dependent reflections generally can pass overhead, but they can converge to the stage, disturbing the performers. Provision for covering stage, performer audibility and directing sound. Moreover, the sound reflected from the tiers of benches, if at a distance, can produce sustained echoes. So, these early reflections are required to happen in the front part of the open-air theater only. We can even determine the pitch of those particular frequencies that will be echoed. This distorts some particular frequencies and may affect sound quality. The echelon effect of auditorium design can happen for this particular kind of corrugated seating too. In OAT, the frequency-dependent reflections, generally, can pass overhead but can converge to the stage, disturbing the performers. Since the seats are circular, they can create a concave effect and can focus sound back to the stage, and the performers can feel this disturbing sound coming from the audience side. It could be helpful if the performer's side has a covering over the stage to cut down the late reflections, which are coming back from the concave surfaces of the seating area. Let's say this is the stage area, and these are the concentric seating. The sound may get reflected back towards the stage area from the back row seats. This can create an echo condition, that is, the source can get back the sound at a later time, as a late reflection from the backseat curvature. As you are gradually moving towards the back, your height is gaining. Hence, an awning or support over the stage can cut down the reflected sound coming towards the stage at a certain height. Thus you can cut down the late reflections happening from the last row of the seating. This convergence of sound towards the stage can be cut down by the help of this awning or the support over the stage. Their dimensions must be calculated as specific to site. Let us now see the conditions for stopping echoes coming towards the audience. A back wall can be created, but if the source sound is hitting directly to the features at the back, maybe a building, a tree, or a line of foliages, they can partially echo it back towards the audience. The building, if made of brick or concrete, will absorb a very small amount of this sound, and the major part of the sound energy will be reflected back, in the form of an echo. In case of trees, it will absorb a portion and will reflect back the remaining portion, depending on the density of foliage over there. The back wall has been raised, and that stops the reflection or return sound. Thus, creating a guard wall at the rear end is very important and has to be built accordingly. If the back wall is too high, it will completely stop echoes. In this case, the sound that is coming from the source will completely move out from the seating zone, which is also not very desirable. It is important to increase the lateral reflections for an open-air theater because on the top we are not allowed to provide any cover. There is no concept of ceiling for an open-air theater. In the figure, a side wall is planned. These side walls can also help in reflecting sound towards the audience, which can be considered as lateral reflections. Nowadays, these side walls are made such that the sound is pushed more towards the audience side. A percentage of the sound energy moves back towards the audience, helping in early reflections or better blending of sound. Hence, this creates a closed space plan. Also, provide door openings in these side walls for people to enter the OAT. Minimal entry through these walls, or in direct entry plan, is a good choice. The entry should be located in such a manner that it does not cut down the lateral reflections in the process. You can also plan for convex or corrugated surfaces along the lateral wall. Here is the open-air theater at IIT Kharagpur. You can see trees at the back, which helps in absorbing some amount of sound as well as reflecting the rest of the sound. You can see the raised stage here, the circular compact seating plan with a gradient, and the lateral walls of varying shapes at the side. This area, you see here, the front part has a folded surface for sound diffusion. This is a curved surface to disperse the sound towards the middle portion of the theater. The sound which is reaching here will disperse in this fashion, blue arrows. These corrugated features will help in diffusing sound towards the audience. Another surface here with a different radius of curvature. Entries are planned at different points. We have a case study of Ansal Plaza at Hudko Place, New Delhi. Let us take a look. A part of Hudco Place built on 35 acres of land, Ansell Plaza is a shopping complex situated near South Extension. A perfect hangout destination, it is built in a circular fashion around an amphitheater with a center stage. Different cultural functions are organized here from time to time, such as fashion shows, live band performances and performing arts to promote the retail area. The circular entity of the building has a special significance. It reflects the individuality of a shopping mall, indicating to the customer that each and every part of the building has something of quality to offer. Leading off from the Blue Bowl and circular Manar, here the central access path at the stepped level, interacting spaces and communicative linkage with nature, generates soothing effect. The area of the amphitheater here is about 3,000 square meters. The semicircular design clearly indicates a fundamental understanding of the spherical propagation of sound, and a desire that every member of an audience should hear equally well what is being intoned on stage. The acoustic advantages of a stepped dish are only optimized, however, when the speaker is standing at the exact center stage. Only then will the voice propagate symmetrically, and reflect back from unoccupied areas to the same point. The surrounding building blocks and the landscaped area in the back of the seating acts the embankment to the amphitheater from the noise coming from the surrounding area. As such, no backstage is provided. The sound appears to spread out when no audience is sitting, and no extra measures have been taken to enhance the sound propagation. The small green areas are provided around the amphitheater, which act as absorbers along the colonnades. The colonnaded feature around the seating area, sound will in this case bounces back and forth between the vertical seat risers, the colonnaded feature and the surrounding built forms. The reverberation sound produced by the reflecting surface of the glass is absorbed by the porous finish of the colonnades. Sound is absorbed by the heavy landscaped area, which acts as buffer zone. The amphitheater is situated in a sound shadow area casted by the surrounding shopping complex and also act as sound barriers. Sound barriers work on the principle of casting a acoustic shadow away from the source. Clearly, if there is line of sight between source and the listener, there is no acoustic shadow and no noise reduction. The glass provided around the amphitheater on the building facade acts as the reflectors. The shape of the theater is such that most of the audience is drawn close to the stage. The colonnades surrounding the amphitheater are used for three purposes. A. Sound absorbers and reflectors due to surface finish material, porous red sandstone. B. Placing of speakers and lights. C. Decoration at the time of events. The slope of the floor is towards the stage, and it is nearly about 12 to 15 degrees to the horizontal, which feels almost flat. The back of the speaker has to be covered at the time of show because of the surrounding parking. Speakers are used for various performances. We can see the placements of the speakers in the picture. Planters at the back acts as absorbers. Varying heights of planters as to break the path of sound as required. Open-air stadium require cut down on reverberations that can interfere with announcements and other speech. In stadiums, designers often use fiberglass and other porous materials to absorb sound. Roof should direct sound to field. Crowd noise in stadiums during moments of high excitement in games is typically between 95 to 105 decibels and even 110 decibels. Steeper grandstands make more noise since the fans are all closer to the playing field. A roof or dome holds noise in and directs it towards the field. Giant open-air bowl configuration dissipates noise. Design thumb rules for an open-air stadium. Nowadays these are covered with fiberglass, ETFE, which is ethylene tetrafluoroethylene, or PTFE, which is polytetrafluoroethylene sheets. And when the crowds cheer or applaud the sportspersons or players, it creates a sound of around 90 to 95 decibels, which may go up to 105 decibels, and occasionally even 110 decibels. Those sounds are all directed towards the field. It's better to have a curvature or a covering which will direct the sound towards the field, then it is fine. Otherwise, this amount of noise will not allow other spectators to listen to the announcements being delivered or on-field discussions made during the game. The ongoing sports performance is intended to be watched by the spectators, rather than being shouted at, but such noise that is produced by the crowd reaches the field. Steeper grandstands make more noise since the fans or spectators are located closer towards the playing field, and the roof or dome holds the noise as it directs the sound towards the field. So, these stadium covering concepts are to be kept in mind while planning for covered open-air stadiums. This presentation is only a compilation of all the relevant information available on the Internet and books. Thanks for watching.